Okay, it's Mathman here, and it's been a very drizzly day, and we haven't had much luck this weekend in the way of weather, so it's a good day to do math. In our last video, we left off at derivatives, and we were taking derivatives of some functions. We made a foray into trigonometric functions. We'll take a look more closely at the derivatives of all of the trigonometric functions. Then we'll take a look at the natural logs, and also the exponentials a little bit more closely. So why don't we move right into it at this point. So we get lined up with the board, and I'm going to get our reference notes here. We have, there we go. So here we go. We're going to take, we're going to start with our trigonometric functions first. And we had derived the derivative for the cosine. Uh-oh, I got a phone call here. Just a second.
I'm back, you know.
Okay, so like I said, we're going to be doing derivatives. We had a grocery delivery done, and so life has changed suddenly.
We did a deliberative.
So, yeah, deliberative. Life has changed so much. But anyway, math hasn't changed at all. And
the numbers on coronavirus.
We're going to be taking a look at how the coronavirus actually follows an exponential change. So anyway, we're looking at derivatives of trigonometric functions, okay? So we started out with the cosine function. We said f of x equals cosine of x. And we were looking at we took a look at the slope along the curve at any point along the cosine function. We said y2 minus y1 over x2 minus x1. And that happens to be cosine of x, or x, plus delta x minus cosine of x on x plus delta x minus x. And that leaves us with, using the trigonometric identities, we've got cosine of x, cosine of delta x minus sine of x. I'm going to give myself a little more room here. Equals, this pen is starting to run out, equals cosine of x, cosine of delta x minus sine of x sine delta x minus cosine of x, all on delta x. And we know that as delta x goes to 0, we say that the limit as delta x goes to 0, well, cosine of delta x as it goes to 0 is 1, so we have cosine of x on delta x minus cosine of x on delta x. So no matter what those are, these cancel out anyway because they're opposites of one another. And we have minus sine of x, sine of delta x on delta x. But as delta x goes to 0, the sine of delta x goes to delta x. So we have delta x over delta x is 1, and we're left with the limit as delta x goes to 0 of delta y over delta x for the cosine function equals minus sine of x. And that's what we're left with. And we did the same thing. Okay, that was for the cosine function. We did the same thing for the sine function. And we found that the derivative of the sine function is the cosine of x, and the positive cosine of x. So we have the two derivatives. So when f of x equals cosine of x.
Our mouse walked off with some peanut butter. I don't know where it is.
The derivative f prime of x equals the minus sine of x. And when f of x is the sine of x, the derivative f prime of x is the cosine of x. Now, we can use these to find the derivatives of the secant, the cosecant, and the tangent. So let's take a look at the secant. Secant of x, when f of x is equal to the secant of x, that's equal to 1 over the cosine of x. That's equal to the cosine of x to the negative 1 power. So when you take the derivative, f prime of x, we use the power law, is equal to minus cosine of x to the negative 2 times negative sine of x. So that's equal to sine of x over cosine of x times the secant of x, and that's equal to tangent x secant x. So the derivative of the secant of x is the tangent x times the secant of x. Now, we're going to look at the cosecant. You can see how these are done. When f of x equals the cosecant of x equals the sine of x to the negative 1 power. And that's a power. That's not a symbol for the arc sign. Sometimes symbols can be misread, especially with trigonometric functions. Sometimes that'll be read as the arc sign. So f prime of x for the cosecant of x is equal to negative sine of x to the negative 2 times the cosine of x. And that happens to be cosine of x, and that's negative, over sine of x times 1 over the sine of x, and that's equal to the cotangent of x times the cosecant of x with the minus sign. All right, so we've done secant, cosecant, and now we'll take a look at the tangent function. The tangent, when f of x equals the tangent of x, that's equal to the sine of x over the cosine of x. And that's equal to the sine of x times the cosine of x to the negative 1 power. So now we use some of those power rules that we learned with the polynomials. So we'll first take a look at cosine of x. Let's say f prime of x equals cosine of x times cosine of x to the negative 1 minus sine of x. Let's get that. Sine of x cosine of x to the negative 2 minus sine of x times minus sine of x. So this is 1, or I'm jumping, let's just say cosine of x over cosine of x, and that's minus is plus, sine squared of x, sine squared of x over cosine squared of x, and that happens to be 1 plus, that's the tangent squared of x. But remember, our identity, cosine squared of x plus sine squared of x equals 1. Well, if we divide through by the cosine of x, we have 1 plus tangent squared of x equals 1 over cosine squared of x, and that's equal to secant squared of x. So this is equal to secant squared of x. So that's the derivative of all of the trigonometric functions. So we can sum them up. We're going to make a table here. We're going to make a table. We're going to have f of x for the trigonometric functions, and we're going to have f prime of x. So cosine of x is the minus sine of x. The sine of x is cosine of x. The secant of x is equal to, I forgot what, I should have written it down. We're going to leave that, cosecant. I think that's tangent x, secant x, and cosecant of x is equal to the negative cotangent of x, cosecant of x, and we got tangent x is equal to secant squared of x. And cotangent x, I believe, is going to be the negative, but let's try that. Cotangent of x. Cotangent Cotangent of x is the only one we didn't do. So cotangent of x is equal to the cosine of x times the sine of x, the negative 1. All right, so we have minus sine x times sine of x, the negative 1, minus cosine of x times sine of x, the negative 2, times cosine of x, and that's equal to minus 1 plus, and this is cotangent squared of x, and that's equal to minus cosecant squared of x. And let's just write that down there for now as a placeholder, cosecant squared of x. And we're just going to make sure that that's the case, because we have, again, cosine of x squared plus sine squared of x equals 1. All right, divide through by sine of x, and we've got cotangent squared of x plus 1 equals cosecant squared of x. So we're right. It's the minus cosecant squared of x. So we have the 1, 2, 3, 4, 5, 6 trigonometric functions. 1, 2, 3, 4, 5, and 6 trigonometric functions and their derivatives. And that's their derivatives. So that's how they come about. You don't need to memorize them. These are things that you can do off of the two functions. As long as you know what the derivative of the cosine function or the sine is, and we went through how you got using the limits of delta x goes to 0, we got the derivative for the cosine of x and the sine of x. And we used those values to come up with these subsequent derivatives. Now, we also looked at e to the x. E to the x, we said, was f of x is equal to e to the x, and f prime of x, and we looked at how you derive that. Whoops, this is a positive e to the x, is simply e to the x again. And we did that by looking at f of x equals e to the x, and delta y over delta x equals e to the x plus delta x minus e to the x over delta x. And now we take the limit, well, x plus delta x minus x, but then these cancel out, and you just are left with delta x. I skipped a step there, and I don't usually like to do that, but last time I didn't skip that step, delta x, and then we have e to the delta x, e to the x minus 1 all over delta x, and then we take the limit as delta x goes to 0 of this function to get the derivative, and that's equal to e to the x, because we can pull that out. The limit of delta x goes to 0 of, well, we can take a look at e to the delta x minus 1 over delta x, and that's equal to e to the x, the limit of 1 over e to the delta x minus, whoops, I got it wrong. I got 1 minus 1 over e to the delta x over delta x, and we have e to the delta x here. And when we look at these limits, make a table, delta x and e to the delta x, and we plug in the values as we go, 0.1, 0.01, 0.001. We see that this whole limit goes to 1, and we're left with e to the x. And so that's how we found this derivative for e to the x. And when f of x is equal to e to the minus x, the derivative is f of x equals minus e to the minus x. So those are the exponential functions that the derivatives of the exponential functions. Now we're going to take a look at something a little different. We're going to take a look at the logarithmic functions. And I'm going to have to 1, 3. Okay, so why don't we start out with f of x equals y equals the natural log of x. So e to the y equals e to the ln of x equals x. So now we take the derivative, we go dx as an operator of e to the y equals dx of x. And that happens to be 1. All right, so we have e to the y. Okay. Remember, we're doing the power function, the g of x times h of x. So here we have d e of y, so that's ey, dy dx. And dy dx equals 1 over e to the y darn it. Oh, dear, dear, dear. But this is just x. E to the y is x. So then we have 1 over x. So dy dx equals 1 over x, when f of x equals ln of x. So that wasn't so bad. We'll run through that one more time. We're going to start again where f of x equals y equals e, ln x, the natural log of x. So if we raise this e to the y on both sides, we have e to the ln x, and that's e to the y equals x. Now, if we take d dx on both sides as an operator, we have d dx of e to the y equals d dx of x. This equals 1, and this one equals e y times dy dx. But then e to the y is just x. So we have x dy dx equals 1, dy dx equals 1 over x. And that's the derivative of the natural log. So that's pretty cool. That's pretty neat stuff, isn't it? I went through it twice because I think that just seeing the flow of it helps. So we've done sine of x, we've done cosine of x, we've done secant of x, we did cosecant of x, we've done tangent of x, the cotangent of x, we've done e to the x, e to the minus x, and ln x. And we've done 1, 2, 3, 4, 5, 6, 7, 8, 9 different functions. And that's pretty cool. Plus polynomials. So we have derivatives for all of these. Yeah, this is derivatives of tangent and the others. Trigonometric functions. Let's see what else have we got. That's pretty cool. All right. So why don't we look at inverse trigonometric functions? And we'll take a look at those. You remember those. We called them the arc sine and arc cosine. And remember when we had a right triangle and we had and we have y, x, and r, and we have cosine of theta equals x over r, and we have sine of theta equals y over r, and the arcsine the arc cosine of theta equals theta equals the arc cosine of x over r. And the same thing, arc sine of theta equals arc sine of y over r. And the same with the tangent. Tangent, remember, tangent theta is equal y over x. And so the arc tangent of theta equals the arc tan of y over x. And so those are the arc sines. And remember, we used notation like this, cosine of theta. We said this is equal to the arc sine, and we use this. But that can be confused. That can be confused with a power. So that is unfortunate that both notations are used. A co or a sine. Sometimes they don't spell out the whole thing like arc. Arc makes it easier to understand. Sometimes it's a little tricky to know when somebody means this is a power, 1 over cosine of theta, versus the arc sine of theta. So you have to be careful when you see this notation. So now let's take a look at some of the derivatives of these. Okay, so we're going to start on the arc sines. So let's start out with y equals the arc sine of x. So if we take this sine of y, that equals to the sine of the arc sine of x, which equals x. So that says sine y equals x. So sine y equals x. Well, the way we would have that is then we're looking at that as y, x, and 1. And the sine of y would be x over 1. And that means this side would be 1 minus x squared. So now we apply the chain rule to this relationship, dy sine y.
She uses the lyric.
Yep. Equal dy dx equals d dx equals 1. We're using this chain rule up here. Well, d dy equals cosine of y, dy dx equals 1. Well, the cosine of y is this over that. So, whoops, cosine of y is equal to square root of 1 minus x squared over 1. That's the opposite over the hypotenuse, or the adjacent over the hypotenuse. And so we have 1 minus x squared dy dx equals 1, and dy dx equals 1 over the square root of 1 minus x squared. So the derivative of the arcsine is 1 over the square root of 1 minus x squared. We can do the same thing for the cosine function. We apply the chain rule to the function y equals the arc cosine of x. So we say cosine of y is equal to the cosine of the arc cosine of x equals x. And what that means is the cosine of y equals x. And if we just draw a right triangle, it says cosine of y, so let's say that's y. Cosine of y equals x, so that's basically, x over 1, which means this side then becomes 1 minus x squared under the square root. So now we apply the chain rule. dy cosine of y dy dx equals d dx of x. And that's equal to 1. And dy of cosine of y is minus sine of y dy dx equals 1. But the sine of y is this over that. So that's minus square root of 1 minus x squared dy dx equals 1. And dy dx is the negative 1 over the square root of 1 minus x squared. And that's it for our arcsines and cosines. We're applying the dy dx equals d dx. That's the chain rule. And so that's pretty cool, pretty neat stuff. So now we have the derivatives of all of the, let's see, trigonometric functions. We have the exponential functions. We have the derivatives of the polynomial rules, the different rules. We have the logarithmic derivative. And now we have the derivatives of the arcsine and arccosine. Let's try the tangent, okay? So we have y equals the arctangent of x. So the tangent of y equals x for the same reasons that we did before. So then we say d dy tangent y equals d dx of x equals 1. And remember, d dy of our tangent was the I think it's a secant squared. Let's work it out. Okay, the tangent theta is equal to sine theta cos theta -1 equals cos theta, and this is d theta of tangent theta equals cosine of theta times cosine of theta minus 1 minus sine theta plus squared cosine theta squared, which is equal to 1 plus tangent squared theta equals secant squared theta. So this was secant squared theta. All right, so if we have tangent y equals x, we have a right triangle. This has to be x, this has to be 1, because tangent y is x. So this here has to be 1 minus x squared. And this is dy dx equals 1. And secant squared is 1 over the square root of 1 minus x squared dy dx equals 1. Dy dx equals well, this just equals 1 minus x squared equals 1 minus x squared. So that is the derivative of the arctangent. And you can do these for the rest of the trigonometric functions. All you have to do is remember that you go back to your basic definition and draw the, when you get to this stage, then you draw your right triangle and you come up with your relationships, so that when you take the derivative of the when you take the operator, the chain rule operator on the function tan y, then I'm sorry, this secant y. There you go. And then we got that. I had the wrong argument in there. But this is the answer. So that's pretty cool stuff. Okay, so let's take a look at the hyperbolic functions. We've got the sinh of x equals e to the x minus e to the minus x on 2. And so if we go d dx of sinh x, we have d dx of e to the x over 2 minus e to the minus x on 2. And that's equal to e to the x on 2 plus e to the minus x on 2. And that's equal to e to the x plus e to the minus x on 2. And that is the cosh of x. And let's see what we've got. Yes, it is. It works out. And I think if we worked out the hyperbolic cosine derivative, we will get similarly the hyperbolic cosine, of x. Whoops. Sorry about that. Okay. Cosh x equals e to the x plus e to the minus x on 2, and dx cosh x equals dx of e to the x plus e to the minus x on 2. And that's equal to e to the x on 2 minus e to the x on 2 minus x. And that's equal to, we put it all over 2, and that's equal to the sinh of x. So there's some similarities in the way they behave, like trigonometric functions in a way. That's why they call them hyperbolic trigonometric functions. They do have some similar properties. And we could go on and on with derivatives. I think you can work out your own hyperbolic, let's say tangent or cotangent, and other hyperbolic functions, and see what they yield. And by applying the rules that we applied here, but so we've looked at all 6 trigonometric functions. We looked at 2 exponential. We took a look at the logarithmic function. We looked at arc functions of the trigonometric functions, and now the hyperbolic functions. So I think we're just going to leave it here. Let's take a look at the hyperbolic tangent. Let's say tangent of x, and that's equal to the sinh x over the cosh x, and that's equal to e to the x minus e to the minus x times e to the x plus e to the minus x to the negative 1. So let's see if this is going to be a little more challenging. So if we go dx of tangent x, hyperbolic tangent x, equals ddx of these, dx of these, e to the x minus e to the minus x times e to the x plus the minus x to the negative 1. And we use our power rules. So we have, we're going to have some space here, so we'll go equals. We got e to the x minus plus e to the minus x times e to the x plus e to the minus x, negative 1, minus 1 times e to the x minus e to the minus x times e to the x plus e to the minus x to the minus 2 times e to the x plus e to the minus x minus. So here we have 1 minus, and this is the hyperbolic tangent squared. And that's it. So that's our f of x prime when f of x equals the tangent of x. So let's see if I had worked that out correctly. Okay, yeah. It's equal to the hyperbolic secant squared. So we went over quite a few different functions tonight. We looked at all 6 trigonometric functions. We looked at the 2 exponential functions. We looked at the natural log. We took the derivative of 3 different arc trigonometric functions and 3 hyperbolic functions. So that's quite a big chunk for one night. So we'll take a look at more derivatives. There are many more to go. But I think we hit on the key ones that we're going to be needing. So for tonight, I'll call it quits, and I wish you all well and stay safe. Don't take any undue chances with the coronavirus. So I wish you all well.